Hey everybody, this is the 2019 FRQ number 2. You'll notice this is a calculator question. So we're given the velocity of particle p, which is the velocity is a differentiable function, and we've got some selected values in the table here. It says for part A, justify why there must be at least one time on this interval where Vp prime, which is the acceleration, equals 0. So we're trying to guarantee that there's some value on this interval where the derivative is equal to 0. So hopefully to you guys, that automatically gets you thinking about the mean value theorem. Anytime we're trying to guarantee that the derivative has a specific value, we need to use the mean value theorem. So let's think about what the conditions are for the mean value theorem. We know that our function, the velocity, has to be continuous and differentiable on the closed interval. And then we need to find the average rate of change over the interval. And then we can decide whether MVT applies or not. So we know that the velocity is differentiable, which means it has to be continuous, because in order for a function to be differentiable, it has to be continuous. So we're actually going to start out by saying, since Vp of t is differentiable, it is continuous. And we do have to specify that part, because in order to use MVT, we have to acknowledge that the function is continuous and differentiable. Now let's find the average rate of change over this interval. So we're going to be looking from zero point 0.3 to 2.8, so over that interval. So we're going to do Vp of 2.8 minus Vp of 0.3 over 2.8 minus 0.3. This is just our regular old slope since it's the average rate of change. So we're going to do 55 minus 55 all over 2.5, and we get 0. So the average rate of change over the interval is 0. The function is continuous and differentiable. That means then that by the mean value theorem, the first derivative has to equal 0 somewhere also. So we're going to say then, by MVT, by mean value theorem, there exists a C on the interval from, let's see, 0.3 to 2.8, such that V prime of C, oops, not T, equals 0. So we can use a huge part of what's actually in the given sentence to help us write this explanation here, which is always a good thing. Okay, then for this question, this was worth 2 points. So it was 1 point for finding the average rate of change. And then it's 1 point for your answer or your explanation. So really, did you show this work here? And then did you write this sentence at the end? All right, moving on to part B, we want to do a trapezoidal sum with these three subintervals to approximate the value of the integral from 0 to 2.8 of VPT dt. So we know for a trapezoid, the area is h over 2, b1 plus b2. So we're just going to do that for each of these intervals. So I'm going to go ahead right away to set this up. Let's see, 0 to 2.8 of VP t dt is approximately, and I'm just going to do the h over 2 part real quick. So the first interval is a height of 0.3, and we're going to need those bases The second one, let's see, that's a distance of 1.4 over 2. And then the final one is a distance of 1.1. So all of those values there are just the heights. It's the distances on the intervals. And now we're just going to look at what the bases are. So from 0 to 2.8. So we're going to be looking at those values there. So 0 plus 55 is going to give us 55. And then let's see, from point 0.3 to 1.7, that's going to give us what, 26? Yeah, 26. And then 1.7 to 2.8 is also, so if I add those two bases together, I also get 26. I know I'm not showing all of my work on there, but hopefully you guys are able to follow along with that. And all we're going to do then is put that in the calculator. So this is going to end up simplifying down to 40.75. And this one was just worth 1 point for your answer. So show your work with your trapezoids a little bit better than I did probably, and get to the final answer. And again, this is a calculator question, so you can just put that right in. Now this part is a little different. So we've got the second particle q that's moving along with this velocity. And it asks us to find the time interval during which the velocity of the particle is at least 60 meters per hour. So we're looking on the interval from 0 to 4, and we want to know, when is VQ of t greater than or equal to 60? So what you're going to do is, in your calculator, you're going to put VQ of t into your calculator and graph it as y1. And then you're going to graph y equals 60 as your y2, and you're going to find the points of intersection, and you're going to see where is it greater than or equal to 60. So I'm going to show you real quick. I've got this on Desmos. The red line that you see here is the velocity function, and then you can see here we've got y equals 60 drawn in with this blue line. So we can see there's almost this like parabola looking shape where the velocity is greater than 60. So find those intersection points. On here it's nice and easy, right? So 1.866 to 3.519. On your calculator, you're going to have to do a little bit more work to find those intersection points, but hopefully you still get to the same answers. So what we can say then is that for this velocity to be greater than or equal to 60, we would have to be on the interval 1.866 to 3.519. Now, this question, I did cut it a little bit. There are some other parts here that won't be on your AP exam this year. And so this portion of the question was only worth 1 point. Did you get the interval or not? There's some other parts to this question. But again, what you're doing is graph this in y1, graph this in y2. And when you do, you'd end up getting, if this is the line y equals 60, I'm going to just sketch that graph real quick. We end up getting something that kind of looks like this. And so we're looking at those two values there. And that's how we get this interval. All right.